When light waves are incident on an interface of two transparent media, light gets partially refracted and partially reflected. Using the Huygens principle, we can derive the laws of refraction and reflection and show that these laws are consistent with the wave nature of light. Let us first consider the refraction of light when it propagates from a rarer medium to a denser medium. Let S' be the boundary of the two transparent media, medium 1 and medium 2, in which the speeds of light are v1 and v2 respectively. Consider a plane wavefront AB in medium 1 that is propagating towards the interface SS'. A normal to the wavefront in the direction of its propagation gives the direction of the wave. Let A' be the direction of the wavefront AB in medium 1. If I is the angle between the wavefront AB in medium 1 and the interface SS', then the angle of incidence is also equal to I. Assume that at t is equal to 0, only point A of the wavefront AB is in contact with the interface SS'. The shape and the location of the wavefront at any subsequent instant of time can be found by constructing secondary wavelets. Since point A is on the interface SS', part of the secondary wavelet originated from this point refracts into medium 2 and a part is reflected back into medium 1. If reflection at the interface is neglected, hemispherical wavefronts from point A propagate into medium 2. As the wavefront travels from medium 1 to medium 2, different points of the wavefront are incident on the interface SS' at different instants of time. If the point B is incident on the interface at C after t seconds, then BC is equal to V1t. Since the speed of the light in medium 2 is V2, during the same period, the secondary wavelet generated at point A at time t is equal to 0, will have formed a hemisphere of radius V2t. Secondary wavelets from different points on the interface form hemispheres of different radii in medium 2. If we construct a plane CD tangential to all these hemispherical secondary wavelets, it would represent the refracted wavefront after t seconds. Note that AD, being the radius of the hemispherical wavelet generated at A, it is equal to V2t, and the direction of AD is the direction of the refracted wave in medium 2. If the angle made by the refracted wavefront CD with the interface SS' is R, then it is same as the angle of refraction. Since angle BAC is equal to I, from the triangle ABC we have sin I is equal to BC by AC. Similarly, as the angle ACD is equal to R, from the triangle ACD we have sin R is equal to AD by AC. From these two equations, we get sin I by sin R is equal to BC by AD. On substituting the values of BC and AD in the equation, and on further simplification, we get sin I by sin R is equal to V1 by V2. Let this be equation 1. We know that if light travels from a rarer medium to a denser medium, it bends towards the normal, and hence the angle of refraction, R, is less than the angle of incidence, I. From equation 1, we can conclude that if R is less than I, then V2 must be less than V1. Thus, according to Huygens wave theory, the speed of light in a denser medium is lesser than the speed of light in a rarer medium. This is in contradiction to the assumptions made by Newton in his corpuscular theory of light. In 1850, it was Foucault who first determined the speed of light experimentally and confirmed that the speed of light indeed is less in water than in air. If c is the speed of light in vacuum, then the refractive index of medium 1, N1, is equal to c by V1, and the refractive index of medium 2, N2, is equal to c by V2. Therefore, N1 by N2 is equal to V2 by V1, which can also be written as V1 by V2 is equal to N2 by N1. Let this be equation 2. From equations 1 and 2, we can write sin I by sin R is equal to N2 by N1. This can also be written as N1 sin I is equal to N2 sin R. This is Snell's law of refraction. Let us now consider the refraction of successive wavefronts at the interface SS'. If the wavefronts as shown represent crests of a wave, then the distance between the two successive wavefronts in a medium is equal to the wavelength of light in the medium. Let the wavelength of light in medium 1 be lambda 1 and in medium 2 be lambda 2. If the wavefront AB is considered, the points A and B reach the points D and C at the same time. As such, the number of wavefronts between B and C is equal to the number of wavefronts between A and D. Therefore, BC by AD is equal to lambda 1 by lambda 2. Since BC is equal to V1t and AD is equal to V2t, we have lambda 1 by lambda 2 is equal to V1 by V2. Let this be equation 3. Equation 3 implies that when a light wave refracts into a denser medium, its wavelength as well as velocity decreases. From equations 1 and 3, we can write sin I by sin R is equal to lambda 1 by lambda 2. In case of light traveling from a denser medium to a rarer medium, the refraction of light is as shown. Using Huygens principle, we can prove equation 1 for refraction of light when it travels from a denser to a rarer medium. Since the speed of light in medium 1 is less than the speed of light in medium 2, the angle of incidence is also less than the angle of refraction. If the angle of incidence I is increased, correspondingly the angle of refraction also increases. For a particular angle of incidence known as critical angle, the angle of refraction becomes 90 degrees and the wave grazes along the interface SS'. If the angle of incidence is greater than the critical angle, we will have total internal reflection. As such, the laws of refraction are consistent with the wave nature of light.